to enable safe collision-free navigation in real dynamic environments. We propose BEV-OSP, a bird's-eye view-based obstacle state prediction framework. It constructs a concise overhead map, learns to predict obstacle states in a latent space, and incorporates an optional sub-goal predictor. Validated across various real-world tests, it achieves robust, collision-free navigation in diverse environments. More details are presented next. First, we validated the effectiveness of our method in a simulated lobby scenario containing 35 pedestrians. During testing, a destination was set arbitrarily, using the 2D nav goal in Reviz, and the robot then proceeded with autonomous navigation. It successfully performed real-time obstacle avoidance and path replanning based on environmental perception. Notably, the robot intelligently adapts its route while pursuing global goals. Our hardware validation began in a controlled indoor setting to assess the system's fundamental navigation capabilities. Firstly, we evaluated the robot's response to static obstacles. To challenge it, we placed multiple boxes in its path, obstacles that were absent from the original map. The robot successfully detected and navigated around them in real time. We then introduced dynamic complexity by adding pedestrians to simulate crowd interaction, where the system demonstrated smooth and safe navigation. Pedestrians were also moving randomly within the testing area, creating opportunities for unstructured interactions. We also arranged for test subjects to walk directly toward the robot at corners, creating deliberate head-on encounters. Finally, within this controlled environment, we tested emergency responsiveness. This involved experimenters abruptly introducing obstacles like boxes into its path or physically intercepting its trajectory. The system responded quickly and effectively to all unexpected obstacles. We now moved the evaluation into more complex real-world environments to test the system's adaptability. The robot executed a long-range navigation task, seamlessly transitioning from an indoor to an outdoor space. This tests its robustness against significant changes in lighting and environmental structure. Next, we challenged the system in a constrained scenario, a long, narrow hallway. To rigorously stress test the system's precision and real-time decision-making, we increased pedestrian density within a long, narrow hallway, which is a crowded and restricted environment. This scenario not only evaluated its navigational accuracy under pressure, but also assessed the agent's ability to generalize across structurally complex and densely populated spaces. The final and most demanding assessment took place in a fully open and unstructured outdoor environment. Here, the robot was required to navigate in a dynamic scene with randomly appearing pedestrians, parked bicycles, and moving e-bikes traveling at various speeds. Experimenters repeatedly stepped into its path to test reactive avoidance. Simultaneously, it handled bicycles and electric scooters that maneuvered with unpredictable trajectories and varied speeds. This mixed traffic scenario served as a comprehensive test of the system's ability to interact and adapt in a dynamic real-world environment. The system faced reliability issues in dynamic outdoor environments, where localization inaccuracies could cause navigation to fail. To address this, we introduced a hybrid planner that augments the global planner with our sub-goal prediction module, automatically switching to predicted waypoints if progress stalls. We also enhanced safety with a recovery mechanism that triggers emergency stops when obstacles are too close, resuming only when the path is clear. Furthermore, we carried out an even more challenging stress test during peak hours in an outdoor setting. Bicycles and electric scooters would appear without warning, passing the robot from both the front and the rear at different speeds, while pedestrians also moved across its path, creating continuous dynamic interference. This test evaluated the robot's ability to interact safely and appropriately with unfamiliar moving agents, while maintaining efficient environmental perception and real-time responsiveness in highly dynamic and crowded conditions. Across all three scenarios, from controlled validation to unstructured outdoor testing, the system demonstrates reliable autonomous navigation, effective real-time obstacle avoidance, and competent multi-agent interaction in complex environments. Finally, thank you for watching.